Devonian period, when this fossil was alive, a day actually lasted 21 hours and 55 minutes. Now, I must admit, I find that really weird. The fact that in the past, a day wasn't 24 hours. The length of a day is simply the time it takes for the Earth to spin once and go from one sunrise to the next. If, in the past, days were shorter, then the Earth must have been spinning faster. In fact, back in time, back billions of years, the planet was spinning so fast that each day lasted just 5 hours. But why should the spin of the Earth have changed over time? Because of the Moon. When the Moon formed, it was so close to the Earth and pulling so hard that it acted as a brake on our planet. By chance, the Earth was spinning this way and the Moon was pulling that way. The net effect was that the Earth slowed down. For billions of years, the gravitational pull of the Moon has been putting a brake on the spin of the Earth, and days have been getting longer. What was once 5 hours now lasts 24. We humans have been around for such a short time, about 200,000 years, that we've only ever known 24-hour days. Our body clocks are completely geared for that length of day, and yet we only have 24-hour days because of the Moon. It's amazing to think that the very rhythms of our planet have been set by this ball of rock out in space. But what about the Moon itself? How has it been affected by the spin of the Earth? Well, one of the first things you learn in physics is that for every action, there is an equal and opposite reaction. As the Earth has been slowing down all these years, something else has been speeding up. And that something is the Moon. For billions of years, it's been getting faster. And what happens to something in orbit as it gets faster? Well, imagine the centre of this roundabout is the Earth, and I'm the Moon in orbit. As we speed up, I get slung outwards, and I feel as if my body wants to move into a wider orbit. And that, more or less, is what's been happening to the Moon. As it's been speeding up, it's also been spiralling outwards into a wider and wider orbit. But is it still spiralling away? Or has it stopped? There's one way to find out. Apache Point Observatory in New Mexico. One of America's largest telescopes. It's also one of the last outposts of the Apollo program. Besides having a lot of fun on the Moon, the Apollo astronauts were running a series of scientific experiments.
Roger, David, looks good to us. Handle down,
And on 3 of the missions, they left behind retro-reflector units, packed with small mirrors. This one is from Apollo 15. And ever since, astronomers have been firing lasers at them to keep track of exactly how far away the Moon is.
So once we're all centered up on Apollo 15, I can open the shutter and we're ready to shine the laser.
Dr. Russet McMillan carries out the laser ranging at Apache Point. So you're now sending pulses of laser light out towards the Moon?
That's right. They're going to travel to the Moon, get reflected, come back, and get detected by our detector.
So how much of the light do we actually get back?
Well, we're sending out about 100 quadrillion photons with each pulse. If we're lucky, For each pulse, we might get back 1 photon.
1 photon back?
1 photon out of 100 quadrillion going out.
A photon is a tiny particle of light, and 100 quadrillion is a phenomenally large number. But by capturing just a few photons, it's possible to measure the distance between the Earth and the Moon, down to the last millimetre.
As of right now, the distance to the Moon is 393,499 kilometers, 257 meters, and 798 millimeters precisely.
Astronomers have been using lasers to measure the Moon's distance for nearly 40 years now. And what they're finding amongst all those photons is a very clear pattern. The Moon, which has been drifting away from us for billions of years, is still drifting at a speed of 3.78 centimetres a year. In human terms, that's about the same speed that our fingernails grow. Does it matter that the Moon is drifting away from us? Well, for one thing, if it keeps going, we'll lose a great natural wonder. One of the benefits of astronomy is you get to stay up very late. And if you don't go to bed at all, you can catch the Moon setting while the sun rises. What an amazing sight. There, the rising sun, and opposite, the setting moon. They both look exactly the same size, but that's an optical illusion. Let's take these two balls. The golf ball is much smaller than the tennis ball, and you can tell that when they're side by side. But if I move the golf ball towards you, you can see it's getting bigger. And at this point, they look to be the same size. Now, it's exactly the same with the sun and the moon. The moon is actually 400 times smaller than the sun, but it's also 400 times closer. And so they appear to be the same size. And that's what gives us the most mesmerising sight. A total eclipse. Because the moon's disk is the same size as the sun's, they line up perfectly, with just a halo of solar gases spilling out around the rim.